we are discussing the mathematical induction, that means the proof techniques that normally we use the mathematical induction. We have already read the normal form as well as the strong form of mathematical induction. Now, today we will see different type of problem, not only mathematical, but other problems, how directly or indirectly we use the mathematical induction. So, this session is the problem solving using mathematical induction techniques. So, first we see one very simple problem. So, find the sum of n consecutive odd numbers. Find the sum of n number of consecutive odd integers. See, normally the problem we see that where we use mathematical induction, that some well known formula or the correct formula is given, and then normally we validate it by induction or we prove that the formula is true. So, for this particular example, that formula is not given. We already discussed this type of problem. So, first we have to find out a correct formula, and normally we do that thing for some taking some primitive values and then to observing the sequences, we try to identify or try to frame one formula for that. So, this is sum of n consecutive odd numbers. If we know that n consecutive numbers are that 1, 3, 5. So, n is 2n minus 1. These are the n consecutive odd integers. And we have to find out the sum. So, I equal to 1 to 2i minus 1 or to n minus 1. Or I can give, or better I write 2 equal to 1 to n to I minus 1. I have to find this sum. Now, if I consider I equal to 1, then the sum say S 1 is only 1. If I equal to 2, S 2 is 1 plus 3 equal to 4. One plus 3 plus 5 is 9. And if we observe the pattern or the sequences, we see that S 1 equal to 1, I can write that as if 1 square. This is for S 2, that is I equal to 2, I can write this is 2 square. For 3, this becomes 3 square. For 4, this becomes 4 square. So, I am getting a compact formula for this. So, I equal to n, this S n is 1 plus 3 plus 5 to 2 n minus 1 is equal to n square. So, first we get a formula that it is n square. Now, we have to prove by induction that this formula is indeed true. That means, if I write that my sum equal to I equal to 1 to n 2 I minus 1 equal to n square, whether this formula is true or not. So, earlier we have seen when we have discussed the mathematical induction, how to get the a correct formula. So, normally this is one of the technique that we get that thing. Now, we have to prove, and we remember that to prove this thing, we have to do the 2 steps we have to follow. One is the basis step. So, basis step, where we consider for I equal to 1, we know the n square equal to 1, and the sum I equal to 1 to 1, 2 I minus 1 equal to 1, which is equal to 1 square. So, my basis step is true, it is true for n I equal to 1. Now, we see the inductive step. Inductive step, we assume that for I equal to n, the proposition is true. In this case, the formula for this sum, the sum I equal to 1 to n 2 I minus 1 equal to n square, that is true, sum is true. We have to prove that for I equal to n plus 1, or we have to show that the equation is true or the formula is true. So, assuming that the for I equal to 1 it is true, and then for I equal to n it is true. So, for I equal to n plus 1, what is our expression? That our expression is I equal to n plus 1 2 I minus 1, and these I can write that I equal to 1 to n 2 I minus 1 plus the value for the for I equal to n plus 1, that means 2 into n plus 1 minus 1. So, this is my last element for I equal to, or the last odd integer when I equal to n plus 1. Now, according to that inductive state, it is true for n. So, this part is the first term is n square and this becomes 2 into n plus 1 minus 1. So, this is n square plus 2 n plus 1, which is nothing but n plus 1 whole square. So, when I equal to n plus 1, again it is giving n plus 1 whole square. So, that means the formula is true for I equal to n plus 1. So, we can write that for all n I equal to 1 to n 2 I minus 1, that means sum of all consecutive integers up to n equal to n square. So, it is proved. So, for all n this formula is true. So, it is proved. So, normally the how we use mathematical induction to prove the simple mathematical formula. Now, we see a different type of example, but where indirectly we can apply the mathematical induction. We take one problem statement that a wheel of fortune has the numbers from 1 to 36. So, wheel of fortune has the numbers from 1 to 36 painted on it in a random manner. Show that regardless of how the numbers are painted, always there are 3 consecutive numbers on the wheel whose total is or sum, it is the sum is 55 or more. So, this is one type of game. I think all of we have seen in some fair somewhere that it is in a see it is a circular wheel and we have only one pointer type. See, so some randomly say I start from 30, then 1, then 17, 9, 2. In this way, some random way it is painted and this is we call that the wheel of fortune. So, it is in this way it is. Now, our and these numbers are in random manner it is printed on the wheel. Now, we have to show that whatever random way or whatever way the numbers are printed on this, there exist 3 consecutive numbers whose numbers are whose total sum is greater than equal to 55. So, we have to show this thing. Now, we use mathematical induction very indirect way to prove this or statement. Okay. So, the solution we do. So, we have 36 integers. So, let x 1, x 2 that x 36 are the or denote the integers printed on the wheel, printed clockwise. That means, now we since our numbers are not in order. So, we consider x 1, x 2, x 36 in order and they denotes the numbers printed clockwise on the wheel. Since the sum of 3 numbers we have to consider. So, we first assume that if we consider that the result is false, that means the sum of 3 consecutive numbers are less than 55. Why? Because the problem statement tells that there exist or there are 3 consecutives, there are 3 consecutive numbers on the wheel whose total sum is 55 or more. If the statement is false, if the statement is false of the result to be proved, statement is false, then for all numbers this sum of 3 consecutive numbers are less than 55. Then the sum of the sum less than sum of 3 numbers, consecutive 3 numbers are less than 55. Now, how many sums are there on a wheel? See, we have 36 sum numbers. Now, I can write that numbers are the way we have taken, as if this is my x 1, this is x 2, x 3, x 4. In this way, I have x 36, x 35, 34. In this way, the 36 numbers are given. So, for the result to be false, all such 3 consecutive numbers, say x 1, x 2, x 3, these 3, then x 2, x 3, x 4, these 3, x 3, x 4, x 5. Similarly, all these numbers, this x 34, x 35, 36, x 35, 36, x 1, then x 36, x 1, x 2. All these consecutive numbers must be less than, sum of these 3 numbers must be less than 55. So, we can write that for the result to be false, since for all sums of 3 consecutive numbers, we have to show that this is false. So, we can write that x 1 plus x 2 plus x 3 less than 55, say x 2 plus x 3 plus x 4 less than 55, x 2 x 3 plus x 4 plus x 5 . We can continue in this way, and in this way x 34, x 35, x 36 less than 55. Then since it is a wheel, that means circular in fashion. So, x 35, x 36 plus x 1, that is again 3 consecutive numbers, then x 36 plus x 1 plus x 2, this is also less than 5. So, these are the all possible sum of 3 consecutive numbers on the wheel, So, how many sums are there? We can see that it starts with variable x 1 or it starts with integer x 2, x 3, x 36. So, there are altogether we have 36 sums. So, we have 36 number of sums. Now, see if we just observe that thing, that means in these 36 sums, each term, each xi appears 3 times. Since it is a sum of consecutive 3 numbers, since it is sum of consecutive 3 numbers. So, in these 36 sums, each term or each integer xi appears 3 times. So, we can write that 36 into x 1 plus 3 into this is, since each one is appearing 3 times, 3 into x 1 plus x 2 plus x 3 all 36, that will be less than 36 into 55, which is less than 36 into 55 is, if we multiply, this is 1980. Now, what is this x 1 to x 36? Because this is the integers, sum of integers 1 to 36 only they are printed on a different order, but when we are taking the sum, these are whatever way we take, this is actually sum of integers, and that should be 1 to 36, that sums are n into n plus 1. So, this sum is, sum of this number is 36 into 37 divided by 2. Is 18 into 37 and this is equal to 666. So, my LHS is 3 into 666 is, this becomes 1998. Now, what we see that this number, this sum of 36 sums, this becomes the 1998. But if it would be, if this is the statement, the first statement we have assumed that for the result to be false, that means for each consecutive number must be less than 55, then it must be less than the all sum of 36 terms must be less than 1980, but what we see that it should be 1998. So, that means our assumption is false. That means, that for this result to be false. So, the conclusion is that we have at least 3 consecutive terms. So, 3 consecutive terms whose sum is or total is greater than equal to 55. See, this is a indirect way that we have actually proved, and this is that these sums, the 36 sums we have written, that is actually by induction, and this is a indirect way of applying the induction. And if we just quickly see one another example, that some mathematical example, say we know the harmonic numbers. How we define that thing? We define that say h k equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by k. Now, there are a number of problems, the number of inequalities, equalities that we can prove on these harmonic numbers. Now, one is we can write that proof that h 2 to the power n is greater than equal to 1 plus n by 2 for all n greater than equal to 0. Here we directly apply our mathematical induction. So, what is our basis steps? So, solution for our basis step, we see for n equal to 0. So, h 2 to the power 0 equal to h 1 equal to 1. So, I can write this is equal to 1 plus 0 by 2. So, this is true. So, our basis step is true. For inductive step, we assume for I equal to n it is true, for I equal to n the result is true. That means, our result is true is that h 2 to the power n greater than equal to 1 plus n by 2, that is true. So, we have to show for I equal to n plus 1. So, I equal to 1 n plus 1 2 to the power n plus 1 greater than equal to 1 plus n plus 1 by 2, that we have to show. Now, what is h 2 to the power n plus 1 by 2? This is 1 plus 1 by 2 plus 1 by 3 plus 1 by n plus 1 by 2 to the power n plus 1 by 2 to the power n plus 1, like that. So, up to this is my h 2 to the power n, this is h 2 to the power n is 1 plus, I can write greater than equal to, this is greater than equal to 1 plus n by 2 plus 1 by 2 to the power n plus 1. Now, how this term I can show? So, our h 2 to the power n plus 1, I can show that this is greater than equal to 1 plus n by 2 plus 1 by 2 to the power n plus 1. So, I can write this thing that because this is up to 2 to the power n. So, this term is if I know that what is our h n, okay, if I consider my h 2 to the power n plus 1, this will be 1 plus 1 by 2 plus 1 by 3 plus 1 by 2 to the power n plus 1 by 2 to the power n plus 1, 1 by 2 to the power n plus 2 plus 1 by 2 to the power n plus 1. So, my h n is only up to this term, and I have these are the terms that I have to add. Now, what are these terms? See, I can write. So, this is my h 2 to the power n plus, see, this is the lowest term. So, when I am giving the greater than equal to, then what I can write? Each term I can replace by 2 to the power n plus 1, since this is my lowest term. So, this is 2 to the power n plus 1 plus 2 to the power n plus 1 plus 2 to the power n plus 1. So, how many terms are there? Since this is h 2 to the power n, this is my h 2 to the power n and the whole term is h 2 to the power n plus 1. That means, here there are 2 to the power n terms are there. So, I can write that 1 plus n by 2 plus 2 to the power n by 2 to the power n plus 1, which is greater than equal to 1 plus n by 2 plus 1 by 2, which is greater than equal to 1 plus n plus 1 by 2. So, for h 2 to the power n plus 1, we show that this is greater than equal to 1 plus n plus 1 by 2. So, this is proved. So, what we have seen that mathematical induction is very the most important proof techniques that we have read, and different type of problems, not only the mathematical things or just to verify the formula, we can also prove or verify the other type of problems where directly or indirectly we can apply the mathematical induction. And in computer science as well as in different fields of other science and engineering streams, mathematical induction is very much required to prove the formulas or to verify the formulas.